here's another thing that stars do. Some stars vary. We talked about eclipsing binaries. That's one way for the brightness of a star to vary periodically. But it turns out that some stars vary intrinsically. And the most famous one by far is Mira. We talked about it later. We talked about it earlier. Mira was discovered to be variable probably earlier, but at least as early as the 16th century. And that is because, as you can see in the two pictures on the right, its luminosity changes dramatically by a factor of 100, with a period that averages to about 332 days, but is variable. And it was discovered by this early astronomer Fabricius. And variable stars are traditionally a regime where what I think someone called citizen scientists have great contributions to make. I will post in the resources links, and if you want to get involved in measuring variable stars, there are lots of interesting challenges, and astronomers are looking to amateurs for data on variable stars. The long period, 332 days, and the luminosity make Mira something called a long period variable. The physics and the modeling of these variable stars is difficult, and Mira is the best known variable star, but not the best understood one. I want to talk about the ones that we understand better, and those are located in something called the instability strip. That's this region on the HR diagram over here, which is almost vertical. It's almost determined by temperature, and most massive stars, the sun will sneak under the instability strip for population 1 stars. There are 3 types of variables in the instability strip. Classic Cepheids, W Virginis variables, which is a fancy way of saying population 2 Cepheid variables, and RR Lyrae variables, which sit in this very narrow region over here. So let's start with, and most stars will cross it as massive stars as part of their horizontal branch evolution. So RR Lyrae variables are very interesting. They have periods of hours, and you can detect them by their spectral signature and by their light curve, by the shape of the light curve. And if you find an RR Lyrae, that's brilliant, because notice that the luminosities of RR Lyrae variables vary by perhaps a factor of 2, and so to within a factor of root 2, you can know the luminosity of a star just by knowing that it's an RR variable. By measuring its brightness, you can now have 2 of the 3 variables that go into our cardinal equation. B equals L over 4 pi d squared. So if you measure the brightness and you know the luminosity from the fact that it's an RR Lyrae, you can figure out the distance. So things whose luminosity is known are very useful. They're called standard candles, and RR Lyrae are not the best standard candles, but they'll serve. And so if you find an RR Lyrae variable in a cluster, you can use that to improve your distance measurement to the entire cluster by using the luminosity of the RR Lyrae variable to conclude. This is sort of improved version of spectroscopic parallax. It has the advantage that variable stars live very high, so RR Lyrae variables are quite luminous objects. They're way more luminous than, say, the sun. Cepheids and their population 2 cousins have periods of days, and modeling those is an interesting problem in physics, and it's worth paying attention to them because they will come in. They will turn into something very useful later. So why is it that stars pulse, at least these that we understand? It was understood rather early that they were not eclipsing binaries. The shape of the light curve, this is from a famous 1931 paper. This is the shape of the light curve of a Cepheid variable. It does not match well onto an eclipsing binary. In fact, if you combine it with this measurement of Doppler shift, so this is roughly the radial velocity of the part of the star that is facing us, you see that what this star is doing is it is not moving towards us and away from us. It's not orbiting. The star is actually pulsing its size. It's growing bigger when the radial velocity is negative. Here the star is expanding and the side near us is approaching us, and then the star contracts and the side near us moves away from us. and then it expands again. And so negative radial velocity here corresponds to expansion, and positive radial velocity to contraction. And what we see is that the star is most luminous right after it's done expanding. And here is a measurement from the spectrum of the effective temperature, and we see that when the star is most luminous, its surface temperature is also highest. Okay, so these are our tips, and the idea for how a star could pulsate, could have a hard time figuring out what size it wants to be, so it bounces back and forth, hence instability, was put forth by Eddington. And the idea is, if you could have roughly a situation where compression increases opacity in some layer of the star, makes it more opaque, then when the star is compressed, that layer will trap energy and be pushed out by the radiation pressure until the star expands, the layer releases its energy, and then the star will contract again because the layer will be transparent, energy will be able to escape. So you have this mechanism for trapping energy. The problem in general is that compression, typically in stars, both compresses material, which increases opacity, but also heats it, and temperature reduces opacity. So the problem was how to find a way to have compression not heat material so that its opacity would increase. And the solution is that under suitable condition, compression ionizes, in this case, helium. And what that means is that some of its energy is spent on heating on ionizing helium, less of it goes to heating the material. This allows the net opacity to increase under compression. Expansion reduces ionization. This is called the Kappa mechanism. And it is this mechanism that drives the pulsations of Cepheid variables. And this determines the boundaries of this instability strip, as models tell us that it is stars in this region that have helium at the suitable temperature for partial ionization, where compression and expansion will change its ionization state, deep enough in the star that it can push a significant amount of the star up when it traps energy, and not so deep in the core that core convection will completely destroy the effect. And so we think we understand Cepheid variables, and we care. The reason we care is a discovery by an American astronomer, Henrietta Leavitt, in 1908, and this is actually her data. This is a plot of, again, magnitude is a logarithmic version of luminosity increasing this way, or not temperature, luminosity, logarithmically, so this is the log of L, plotted versus the logarithm of the period. Remember, the periods of Cepheid variables are days. They vary from a day to 50 or 60 or 90 days. And what she noticed is that the longer period variables were the more luminous ones. And she was plotting this for stars in the Small Magellanic Cloud. Again, all of the stars she saw were approximately the same distance. So she could use brightness as a relative brightness as a surrogate for relative luminosity. So she couldn't scale this plot, but she saw that luminosity grew with period. And if you only knew the luminosity of some of these stars, you could calibrate this. And this was calibrated by measuring against globular clusters, which by methods of cluster fitting and spectroscopic parallax and other cluster dynamical ways of measuring distance, the distances to globular clusters were quite well known. Their globular clusters have lots of stars. They had lots of Cepheid variables. And using that, you could use measurement of the period to measure the luminosity, to predict the luminosity of a Cepheid. And again, once you have the luminosity, you measure the brightness. You're using this as a standard candle. Cepheids become a great tool for distance measurement. Again, if you know the luminosity and the brightness, you can compute a distance. Now, it turns out a little bit later that these are population 1 Cepheids in the Large Magellanic Cloud. In globular clusters, we find population 2 Cepheids, or W Virginis variables. Those have a period luminosity relation, but at the same period, the globular cluster population 2 Cepheids are less luminous. So what we have here is a recent paper which made this comparison. We have here the scatter plot here. These are the Small Magellanic Cloud Cepheids, the same ones that Leavitt measured. And down here are globular cluster Cepheids, or population 2 Cepheids. And we see that there is a relation between luminosity and period, but at the same period, a globular cluster, a type population 2 Cepheid variable, is less luminous than the corresponding population 1 Cepheid variable. That too will play a role in what's to come. What we've discovered is another important step on our cosmic distance ladder. We'll use that, and we are in Leavitt's debt forever.